This chart shows the access latency versus storage capacity across a modern computer's memory hierarchy. A massive 3D solid-state drive can hold terabytes in long-term data, but accessing that array takes about 50 microseconds. For a processor executing operations in a matter of nanoseconds, 50 microseconds is a severe latency bottleneck. To bridge this gap, systems rely on dynamic random access memory, or DRAM. This acts as the CPU's main working memory, physically constructed as a two-dimensional array of billions of microscopic capacitor cells. Extracting a specific 8-bit cluster from an array of 17 billion individual cells requires an exact spatial routing operation. The map for that routing is a 31-bit physical address, generated by the CPU's memory controller to navigate this vast microarchitecture. Achieving a 17 nanosecond response time relies on rigorous spatial routing and electrical engineering. We are going to decode exactly how this works by following a single 31-bit address all the way down to the silicon. The journey of our address begins at the memory controller inside the processor, which physically connects to the DRAM modules via two independent memory channels, Channel A and Channel B, routed through the motherboard. Each memory channel operates in parallel, carrying 32 data wires, 21 address wires, and 7 control signal wires. This diagram shows a DDR5 die partitioned into 8 bank groups, each containing 4 banks. In the first stage of decoding, the controller consumes the first 5 bits of our 31-bit address to select a specific bank. Inside that selected bank lies a massive internal array, standing 65,536 rows tall by 8,192 columns wide. Partitioning the die into 32 distinct banks allows multiple rows across different banks to remain open concurrently. If the CPU requests data from an already open row, it registers a row hit and skips the activation sequence, saving considerable time. Subdividing the architecture prevents system-wide bottlenecks. The CPU can execute a physical refresh operation on one bank while simultaneously reading active data from another. With the bank isolated, the next 16 bits of the address are routed into a row decoder. This combination activates a single specific word line out of the 65,000 available in the bank. This illustrates the building block of DRAM at the nanometer scale, the 1T1C architecture, consisting of one access transistor and one capacitor. The word line wire connects to the gate of the transistor, which isolates a deep trench dug directly into the silicon. Binary data is physically stored here. If the trench capacitor is charged to roughly 1.4 volts, it equals a binary 1. 0 volts equals a binary 0. Because the access transistor is only a few dozen nanometers wide, it introduces a physical vulnerability. Over time, electrons physically leak across the closed channel barrier. If left alone, the stored voltage of a binary 1 will slowly drain into a binary 0, resulting in total data corruption. To maintain integrity, the memory controller executes a continuous refresh protocol. Every 64 milliseconds, it must systematically close, pre-charge, and reopen every single row to refill the lost electrons. DRAM operates as an inherently unstable system, consuming massive power and logic overhead simply to prevent its physical data from vanishing. Before a read operation can extract data, the long bit line wire running vertically through the array must be meticulously pre-charged to exactly 0.5 volts. When the word line activates the transistor, the microscopic capacitor connects to the massive bit line.
The stored charge is so microscopic compared to the long bit line wire that it is subjected to heavy parasitic capacitance. The capacitor can only shift the bit line voltage by a minute fraction of a volt. Left alone, this perturbation would be lost to electrical noise. A sense amplifier is required at the end of the wire to detect that minute upward tick and forcefully drive the entire bit line up to a full 1.0 volt. Once the sense amplifiers have driven all 8,000 columns to their absolute 1 or 0 states, the row is officially considered open. Extracting a signal in 17 nanoseconds requires this highly sensitive analog amplification to overcome the limitations of nanoscopic data storage. With the entire row open and amplified, the final 10 bits of the physical address are sent to the column multiplexer at the bottom of the array. This flowchart illustrates the DDR5 approach. Rather than pulling 8 bits out directly, Modern memory extracts high-throughput sequential data by routing into a temporary burst buffer. The first 6 bits of the column address instruct the multiplexer to isolate 128 specific bit lines, loading them into the burst buffer simultaneously. The remaining 4 bits of the address are used to rapidly cycle through that buffer, pushing out 16 distinct sets of 8 bits onto the data wires, heading back to the CPU. This structural layout guarantees massive data throughput for sequential assets, like 3D textures in a game, while maintaining the granularity to address highly specific memory locations. Burst buffers bypass the bottleneck of the narrow 32-bit memory channel by pre-packaging larger physical sections of the array into rapid sequential bursts. Operating a chip crammed with billions of fluctuating electrical signals introduces a final problem: protecting the delicate microvolt read perturbation from ambient noise. This schematic details the folded BRAM layout. The architecture doubles the number of bit lines so that every column utilizes a differential pair, an active line and a passive line, routed into a cross-coupled inverter. If the active bit line is driven to a 1, the cross-coupled inverter forces the adjacent passive bit line to a 0, creating equal and opposite charges. Running a differential pair provides extreme noise immunity, a sharp reduction in stray parasitic capacitance, and a rapid mechanism for settling back to the 0.5-volt precharge phase. At the nanometer scale, memory layout is a highly active differential environment, designed to defeat the laws of physics that constantly threaten to corrupt data. In 17 nanoseconds, the read signal pushes out of the cross-coupled inverter, clears the bank array, travels down the motherboard channels, and arrives back at the CPU. High-speed memory relies on extreme spatial pipelining. That single 31-bit address provides the precise instructions needed to navigate bank concurrency, overpower electron leakage, and utilize burst buffers. This hardware reality directly impacts software logic. If a program forces the memory controller to continuously open and close different rows, it causes thrashing. Forcing the hardware through the row activation sequence over and over destroys latency. Because of the time required to activate these physical rows, modern compilers and game engines prioritize contiguous memory allocation. Keeping data physically adjacent in the same row exploits row hits and maximizes the efficiency of the burst buffers. Understanding the physical truth of DDR5 architecture bridges the gap between hardware engineering and software optimization. Code is ultimately bound by the physical limits of electrons moving through silicon.